Hello and welcome back to the lab. Today on the bench we have, actually it is a GPSDO and it is a 10 megahertz sine wave, and the seller's SKU ID is 68431. When I was doing some lab references and things like that, I had some requests from viewers to test out various GPSDOs just to see how good they are. I didn't have a frequency counter that I considered good enough at the time, so I haven't done the testing yet. May have been for the 2,000 subscriber video. We picked up a Keysight 53230A. Does a lot of data collection, things like that, and very advanced features for a universal frequency counter and timer. It has a 20 picosecond capture window, can do continuous capture, and it can do 350 megahertz native. So plenty powerful enough to evaluate GPSDOs. The other thing that it can do is part of the math and statistic functions of that frequency counter is it can calculate Allen variance, which is a great way of looking at the stability of oscillators over time. So, because we have a counter now that is accurate enough with the rubidium in the lab as a time base, that we could really give these GPSDOs their, we can get some valuable data on it. I didn't have time bases, weren't good enough, counter wasn't good enough, and we've been slowly stair-stepping up the capabilities. So we can now start looking at these. This is the first video of this one. This is the one that came in first. I did get the BG7G, I think. Let me check. The other oscillator that I ordered, which was the requested one, was a BG7 TBL oscillator unit. So we're going to check both. This is just the one that happened to come in first. This one was a little bit less expensive. This unit clocked in at under $100 US. This particular unit, once I test it and evaluate it, unless there's a reason to keep it in the lab, would be surplus to my needs, because I have a GPSDO and a rubidium standard for the lab. So it might be available, unless there's a compelling reason for me to keep multiple GPSDOs. So let's see what comes in the box. We have a power brick. We have the GPSDO itself, which appears to have SMA connectors on it, so I may need to order some cable here real fast. So we have power tracking, GNSS, and communication, and we do have a USB port. 1 pulse per second out, 10 megahertz, and antenna in. So that's not too awful. USB connection. It does come with a GPS patch antenna. We are not going to use that. I have a antenna splitter hiding behind the bench that has GPS output. It's hooked up to an external GPS antenna. So we'll give this unit the best chance it's got to be stable. Let it see as many satellites as it can. And it can actually use the same GPS antenna that my unit in the lab uses. And we'll go from there. This is a 5 volt 2 amp power supply. Not too terrible. We'll see what kind of data we can get out of this thing on a computer too, possibly. All right, let's see what I have for cable. Okay, order came in, and we needed to get some longer SMA cables and some SMA to BNC adapters. One of the drawbacks of the TM4313, at least for my lab, is it has SMAs on the back, not BNCs. So I need to convert some stuff to BNC, but we'll get this stuff hooked up and then we'll let it settle. All right, we've got the unit hooked up to the GPS satellites. So we're going to let this thing start up and see what the front panel does. We have some blue LEDs. I think what's going to happen is when it sees satellites, GNSS should light up, and then track is going to blink. There is zero documentation as to what these lights mean on the front of this unit. So I don't know if it's supposed to go solid when it locks or if it blinks when it locks and it's tracking when it's blinking. I have no idea what's going on with this one. To give it the best chance for stability, because GPSDOs, as they warm up, all right, we see satellites already. As they warm up, they get more and more and more stable. So before we take the measurements and we evaluate this unit, we'll let it burn on the bench for 24 hours. Through the magic of the camera, that's going to take all of about 10 seconds for you guys, but for me, it'll be tomorrow when I come back, because I'm going to let this go until end of day tomorrow, and then we'll set up the function or the frequency counter and take a look at the stability. Take a quick look at how this looks like on the oscilloscope. We have a 3-volt amplitude coming out and pretty decent stability, at least for the scope, 10.0001. The time base in this scope isn't the greatest, so I would not use that for frequency analysis, but our sine wave looks nice and clean. Everything looks good. Doesn't look like it's drifting too much. Doesn't say that it's tracking yet, so it still might be trying to lock. So we're just going to keep an eye on it and see how it goes. Okay, we'll take a look at the signal on one of my spectrum analyzers. This is the 10 megahertz output coming out of the TM4313. And what we would, ideally, what we'd like to see is all the energy right here at 10 megahertz. But we have these skirts that come down. These are pretty steep, not too terrible. Since the marker position right now is 15 dBm, and we go down to negative 85 dBm. So we're actually seeing a very good signal coming out of this thing. Not too bad. Allen deviation is going to measure all of the noise of this particular oscillator in a very good way, and it's going to allow us to quantify the signal in a way that's rather helpful. So we'll look at peak-to-peak variance of the signal. We'll also look at Allen deviation and get into that. But ideally, for an oscillator, you'd want these skirts to be as thin as possible, because that puts the most amount of energy at 10 megahertz. So we do have a little bit going on, things like that. We can fire the sweep off again. And we can see how slow this is actually sweeping. So this wouldn't catch any of the noise that we're looking for with the ADEV number, which we're going to generate here in a little bit. I'm just waiting on the frequency counter to warm up. And we'll get started in on that. Okay, to set up the frequency counter for this measurement, we're going to go to the trigger, and readings per trigger, we're going to do 100 readings per trigger, and we're also going to set the trigger to manual. So when I hit the trigger button, it's going to start a process that's going to take 100 average or 100 readings, and that's going to give us some of our numbers. The next thing we're going to do is we're going to go into math and turn on statistics. We're going to do Allen deviation. We're going to turn statistics on. Then we're going to go to gate, and we're going to do a gate time of 100 milliseconds. So we're actually going to do this backwards. We're going to do fastest to slowest. And on this GPSDO, we're going to see gate time noises and a few other things. Not gate time noise, sorry. We're going to see time scale noise. So we're going to take a look at the Allen variance in several points. And it's going to show kind of why I've decided in the lab to have a GPSDO and a rubidium standard. Now, one of my purposes in the lab, I needed to calibrate calibration gear. So I needed a very, very stable clock reference for the equipment. This might be stable enough for what some of the viewers of the channel are doing. In that case, you do not need to go down the rubidium route. The GPSDO may be just fine. We'll also take a look at another device that has a crystal oven that wanders all over the place that was actually calibration equipment. So we'll get into some fun. That'll be a separate video. Actually, it looks like because the counter's fast enough, we're going to dial this back to 0.01, and we're going to hit it a couple of times. So I need to let this finish warming up, and then we're going to do 0.01, 0.1, 1, and 10 seconds gate time. The GPSDO has had a 24-hour warm-up time. The frequency counter is going to get its 30 minutes warm-up time, but it's stabilized by the rubidium, which has been on for months. It is at its highest stability, locked to the 1 PPS, and everything should be good. Okay, well, we're going to go back to math, reset the statistics, which is good. Because we're doing 100 samples and our gate time is going to change, each time we up the gate time, it's going to take exponentially longer to run. At 10 seconds, it's going to take almost a day to take the measurements. So I'm not going to run the camera for that entire amount of time. You guys will get the Cliff's Notes. Okay, so we're set to Allen deviation. Statistics are on. And we'll hit the trigger button. And there it goes. So with a gate time of 0.01, Allen deviation is going to be 2.529706748111312 millihertz with a peak-to-peak deviation. I need to go back to math. Oh, wow, of a much larger. 15.348, 501, 503, 467, 6. All right, next data point, reset the stats. Going to go to gate, and gate time is going to go up. And we're going to go to 100 milliseconds, so 0.1. And then we're going to go back to math. No smoothing. Math. Oh, yeah. Statistics. Trigger. And what we should see is as these go, the deviation should get better because we're outside of the noise characteristics of the GPSDO. We're getting into longer and longer and longer time scales. So our peak-to-peak deviation and as well as our Allen deviation should improve. I have the 1 second counter going right now, and as we can see, the counts are taking significantly longer to count up. Zoom in so you guys can see what the counter is doing. Okay, we're into the long one. This is with a 10-second gate time and 100 samples. So you guys can watch up here where it says gate, how long it's going to take for a single sample. All right, that's 2 samples from that time period. So we're just going to let this totalize because this is going to take, I think, 0.69 days. So I'll have some numbers in the morning, I think. But this is where the GPSDO is really going to shine, is on these long time scales. Now the problem is, if it's wiggling like this and you're using it as a reference for, say, a frequency counter or something like that, on a long time scale, it's not ultimately going to matter because everything's going to average out. If you have a real narrow gate window and your reference is bouncing around, it's going to throw the reading of the unit off. So a lot of this comes down to what we're measuring, how we're measuring it, and going forward from there and finding the best solution. So what I've found so far is short-term timescales having an atomic standard is good. The problem with the atomic standards is, on a long-term time scale, months, years, weeks, months, years, they drift around a little bit, so they don't stay around 10 megahertz. So on a short-term time scale, GPSDOs hop around a bunch. On a long-term time scale, they're very, very stable. Atomic standards, rubidium, cesium, things like that, are the opposite. Short-term time scale, very stable. Long-term, they meander down the road. Having both gives us the best of both worlds. We have a very stable short-term atomic standard, but we have a very stable long-term 10 megahertz reference disciplining the atomic standard. Now, one of the ways it does that is because of the servoing in the atomic standard. Its servo circuit is using about 7 hours of averaging 1 pulse per second to lock to 10 megahertz. So we're not even using directly 10 megahertz. It's pulsing, and then it's slowly adjusting itself to be within as best it can. Now, from my observations in the software, that is ticking around 3 nanoseconds plus or minus. So it'll drift underneath about 3 nanoseconds from the edge. It'll drift over 3 nanoseconds from the edge. But it really stays around that 3 nanoseconds, and it meanders there by the day. Doesn't change on me very often. So it's wonderful for references for frequency counters, spectrum analyzers, RF gear, things like that. Even my HP function generator uses it as a reference input, and my function generators from Rigel on the bench. So that is partially how we got from point A to point B. The nice thing about this is, even though we are well into the noise, right? So we're very much splitting, well, ultimately millihertz and microhertz at this point. This might be good. Like, the GPSDOs are much better than some of the clocks that are in the function generators, especially the stuff that can come in from secondary market, where they're untested, unvalidated, and need to be aligned and calibrated. Doing that can be kind of difficult without having highly accurate clocks and references, but it is doable. But if you do an external reference, you can tighten up the clocks on those internal devices by quite a bit without a very heavy lift. So there we go, just putting the information out there. And some results for the 100 seconds gate time. Everything looks pretty good. Taking a look inside, we have our GPS module here. This will be the crystal. And then we have some power filtering and other electronics. Rather simple design. 2 important pieces of it, other than having nice clean power rails. Definitely going to be the GPS module. See if we can get a part number on that. It's an ATGM 332D. And then this is a CTI part. This is a CTI part, 10 megahertz crystal reference. Nice bulky capacitors, 470 microfarads, so we have a lot of decoupling. Everything looks relatively good. Looks like the main processor is an NXP part number. LPC 1752 F8080. Okay, here's some of the numbers. We did get into the microhertz for Allen deviation with 10-second gate time and 100-second gate time. We got a little bit better with a 10-second gate time. Actually, we got 1-second gate time. Looks like it got us the best Allen deviation. So this is wandering and meandering quite a lot. But our peak-to-peak frequency variance, we did get into the microhertz on the 100-second gate time averages. So we got 607 microhertz peak-to-peak. We were in millihertz otherwise, which still is not bad. I mean, we're, even at its worst case, we're at 2 millihertz Allen deviation and 15 millihertz with a 10 millisecond gate time. So quite a good oscillator, as long as you don't need ultra precision. Will definitely get the job done. To put some of these numbers into perspective, the rubidium unit in the lab gets down into the 9 microhertz. So if I hook up one of my function generators that's stabilized to the rubidium, run this same test on it, we'll see 9 and some change microhertz. So it is several orders of magnitude better, but it's also several orders of magnitude more expensive. So I can't be the judge if you want to go this far. If you do, I did. But if this is good enough, then this is a great place to stop, and these are relatively affordable. They do benefit from having an antenna outside, though. The more satellites it can see, the more stable it's going to be. So I will be keeping record of this Excel document, and I'll be posting it online in a few places for people to find out. It's going to go up with this video on Patreon if anybody would like to see the numbers in detail. I'm going to I have another oscillator we're going to run through the exact same testing, so we're going to just add model numbers as we go through it. Now, this is not representative of the entire field of oscillators. This is not a specification for this particular unit. This is just characterization and testing of this unit itself. So I can make no claims to any other unit, and I'm not even specifying anything like that. That is just how this particular GPSDO performed. With that being said, I hope this was helpful. As always, I check the comments between videos, and more is always on the way. Patreons are running about 4 videos ahead, so if you'd like to get a little bit more content, take a look over there, see if there's anything interesting. Hit the subscribe, and bell buttons, and stick around. There's far more to come. And I will see everyone in the next video.